Here is a pretty cool realization. You already know everything you need to know in order to understand the Fourier transform and how the Fourier transform works. You learned about sine waves and complex numbers and the dot product. You learned how to integrate these concepts to complex sine waves and the complex dot product. And now we are ready to learn about Fourier coefficients, which is nothing more than a complex dot product with a complex sine wave or a set of complex sine waves and the signal. So you already know all about Fourier coefficients, you just don't know it yet. So what I'm going to do in this video is just put all the pieces together and make you realize that the Fourier transform is a fairly straightforward concept. All right, so let's begin. Here we have a signal, it's some time domain signal. Imagine it's some EEG data or whatever it is. And the idea of the Fourier transform is that we take a sine wave at a particular frequency, line up the sine wave with the signal, and then we compute the dot product between the sine wave and the signal. Now that already implies a couple of important things. First of all, it means that the sine wave needs to be discretized. So the sine wave has to be sampled at the same sampling rate as the signal. And secondly, it also means that the number of time points in the sine wave is the same as the number of time points in the signal. And why is that the case? Right, that is the case because we want to compute the dot product between the sine wave and the signal, and that dot product is valid only when both vectors, in this case the signal and the sine wave, have the same number of numbers, so the same dimensionality. Now you can imagine that the dot product between this sine wave and the signal is going to be large because they look really, really similar to each other. They are almost the same signal. And the magnitude of that dot product gets plotted on the y-axis at the x-axis location corresponding to the frequency of this sine wave. Now, you learned a few videos ago that the dot product, the real value dot product between the sine wave and the signal is very much dependent on the phase of the signal with the sine wave. So for example, if we were to use this orange sine wave instead of this cyan sine wave, then the dot product is not going to be as large. And that is why we need to use a complex valued sine wave and not just a real valued sine wave. The complex valued sine wave accounts for any possible phase relationship between the signal and the complex valued sine wave. And that phase offset is handled because the signal is going to look something like the cosine and something like the sine. So then we just combine the two. We combine the correlation with the cosine and the correlation with the sine. And together that gives us two components to the dot product, one corresponding to the cosine and one corresponding to the sine. And then you saw in the illustration in MATLAB for complex dot products that the combination of the two, the cosine and the sine as a complex sine wave, helps us account for this phase difference. Okay, so then what we do is we move on to another frequency. So we compute the dot product between a complex sine wave and the signal at some frequency, and then we move on to some other frequency. Let's say it's this frequency. Now, this sine wave is a lot faster than the dominant spectral characteristics that you see in this blue signal. So therefore, the dot product, the magnitude of the dot product with this yellow sine wave is going to be smaller. So we plot that on the y-axis at the location on the x-axis corresponding to the frequency of this sine wave. And then this procedure gets repeated for lots of sine waves. So how many sine waves there are and what are the exact frequencies of those sine waves, that is not arbitrary. That's not something that we just get to pick. That is, in fact, determined by the features of the signal, including the number of time points in the signal and the sampling rate. That is an important but more subtle feature of the Fourier transform, and I'm going to talk about that in a few videos from now. So for now, suffice it to say that the big idea of the Fourier transform is that we start with our signal, we create a collection, a series of complex sine waves, we compute the dot product between each complex sine wave and the signal, and then we extract the magnitude of the dot product, the complex dot product, and plot that magnitude on the y-axis at the x-axis location of the sine wave. So I'd like to talk a little bit more about interpreting this complex dot product. So let's think about a high-dimensional space where each dimension, each axis, is defined by a single time point. So this is time point 1, time point 2, and so on, up to time point n. So if you have a signal that has, let's say, 700 time points in it, then this is going to be a 700-dimensional space. And the value along each axis corresponds to the millivolt or microvolt, or whatever the units are of the data, the microvolt value at that single time point. So now when we plot the data, we can conceptualize one time series of data as being one vector in this space. And so the projection of that vector along the t1 axis is the microvolt value at time point 1, the microvolt value at time point 2, and so on. And that gives us one single vector in this high-dimensional space. And then we have the sine wave, which is just some other vector that's pointing somewhere else in this space. Now, I can already warn you that it's a little bit more complicated than this, because the signal is a real-valued signal, and so this is a real-valued space. The complex sine wave is actually not living in this real-valued space. It's in a complex-valued space. So in truth, it's a little bit hairier than this diagram, but for the conceptualization, it's still fine. So now we have these two vectors here, the signal and the sine wave, and we compute the dot product between them. And a few videos ago, I showed you this formula. This is the geometric perspective of the dot product. So here we have the dot product. It's a single number, and it is the magnitude of vector A, which is the signal, times the magnitude of vector B, which is the complex sine wave, times the cosine of the angle between them. So this is now pretty interesting to think about, because for different sine waves, so different sine waves at different frequencies, the signal is never changing. So this quantity always stays the same. B always stays the same as well. So the magnitude of the sine wave is always the same, regardless of where it's pointing in this space. The only thing that differs between the signal and the sine waves of different frequencies is that this vector is pointing off in some other direction. So therefore, the difference across different frequencies, which is the resulting dot product, is determined by the cosine of the angle between these two vectors. And remember, A, this vector A, and here, that's the signal. It's never changing for different frequencies. And B, this magnitude isn't changing for different frequencies. Only the direction of B, this vector here, this complex sine wave, is changing. So then A is a complex number. That's also why things are actually, in reality, a little bit more complicated than what I'm explaining here, because this is going to be a complex angle, but that's okay. We can leave some of the subtle details aside and focus on the big conceptual picture. So we get the resulting complex dot product, which we can conceptualize as a point, as a coordinate, a location on this complex plane. And then we can apply Euler's formula and extract the magnitude and the phase, the angle, of this vector. And we can represent that using Euler's notation, so m times e to the I theta. And we call this thing, which is this thing, a Fourier coefficient. So the Fourier coefficient is really nothing more than the complex dot product between the signal and the complex sine wave at some particular frequency. And then we take this value m, this quantity, which is the distance away from the origin, and we call that the amplitude at the frequency of this sine wave, and this parameter here, phase, which is literally just this angle here, that we call the phase of the Fourier coefficient at that sine wave frequency. So now when we repeat this procedure for many different sine wave frequencies, that allows us to extract one amplitude parameter per frequency, And that's how we build up the amplitude spectrum of the Fourier transform. Okay, so what you see in this slide is a bit of pseudocode. And this pseudocode shows how to implement the discrete time Fourier transform in a loop. So here's what we do. We loop over the number of time points in the signal. And it turns out that the number of time points in the signal determines the number of frequencies that we can extract from the signal. I'm going to explain this in more detail in a later video. So for now, you can just take this as a given and it will be explained in more detail soon. So what do we do inside this loop? So we create a complex sine wave that has the same length of the signal. Now, we already know that the length of the complex sine wave has to be the length of the signal because we need to compute the dot product. And the frequency of the sine wave corresponds to the looping index -1. So that means that when we first start running through this loop, the looping index equals 1, and then the frequency is going to be that -1, which is 0. So we start off with a sine wave frequency of 0. That's called the DC or direct current component or the zero frequency component. I'm going to talk more about that in a later video in this section. So we create this complex sine wave and then we compute the dot product between that complex sine wave and the signal. And the output of this dot product is called the Fourier coefficient for this particular frequency. So then once you've looped through all of the possible frequencies that you can extract, which corresponds to the total number of time points in the signal, then the amplitude spectrum is the magnitude of the Fourier coefficients, and the phase spectrum is the angle of the Fourier coefficients. And this right here is the basis of the Fourier transform. This is how you implement the Fourier transform. Now, if some aspects of this concept, what I've explained in this video, still seem a little bit mysterious, then don't worry, it's totally natural. There's a lot more to talk about the Fourier transform. I'm going to have many more videos in this section that will explain basically this slide in a lot more detail. There's a lot of important subtleties, but this is the basic idea.